Okay, in this video I want to start talking about imaginary and complex numbers. Okay, let's consider first this equation, z squared equals -1. Observe that this equation here has no solutions in the real numbers. Since, if you think about it, take any real number and square it, I get a number that's greater than or equal to 0. Okay, so how could it equal -1? Well, that would be impossible for a real number. So what we're going to do is just invent a new number, I, that satisfies this condition. And we will actually justify this construction later on and show you that the mathematical game of using I is perfectly consistent, okay? And that's all we really need in mathematics is consistency, and we can play the game here, okay? So the fundamental definition here for I, or the fundamental equation it satisfies, is I squared is equal to -1. Okay, we will also write this. I is the square root of -1. That's often done. Okay, so we think of I as being the square root of -1. Okay, not a real number. There's no such thing. It's a completely new number. Square roots of negative real numbers. Okay, we ran into this problem when we were talking about some quadratic equations in the previous video here. Let's say a is greater than 0, and that is a real number, okay? So it's a real number greater than 0. Then the square root of negative a, of course is negative, is going to be defined to be this. It's the square root of a, okay, so that would be a real value, times I, and some people, to save space, would actually do this, or save ink. They would write the I in front, I times the square root of a. Okay, so this is how we define the square roots of negative real numbers. Okay, this is a unique value. Okay, so you only get a single answer. Okay, no plus minus or anything like that. Just like when you're taking regular square roots. Okay, let's take an example here. Okay, if I was going to take the square root of -9, then I'm going to have I times the square root of 9. Now the square root of 9 is 3, so that's I times 3, or better written 3I, okay? You can actually square 3I, and if you think about it, 3 squared is 9, I squared is -1, right? 9 times -1 is -9 here. Alrighty, how about this one? This example, the square root of -1/4, that's going to be I times the square root of 1/4. The square root of 1/4 is a half, so that is really 1/2 I. Okay? All right. Like I stated before, these square roots are uniquely valued, okay? So you only get one answer. But I do want you to notice here that if I have -I squared here, and I'm expecting these numbers to follow the same rules as otherwise, as regular real numbers here, then -I squared should be -1 squared I squared, but -1 squared is +1, right? A negative squared is a positive, so it should be what? -I squared. I squared is -1, so I go plus -1 or -1 also. Likewise, if I have -3I, okay, -3I, that would be -3 squared I squared. -3 squared is 9. 9 times -1 is -9 also. Okay, so with this in mind, consider the following here. Okay, if I say find all solutions to this equation, z squared equals -16, then the answer is plus or minus the square root of -16. The answers, I should say, if you want. Okay. All right. Z is plus or minus the square root of -16. And we can see that the square root of -16 ought to be 4i. So it's plus or minus 4i. Indeed, if we square both of those quantities, we will get -16. Okay, so what I'm doing is showing you the difference between what? The square root of -16, which is what? 4i, versus what? The set of all solutions to the equation z squared equals -16. The set of all solutions to z squared equals -16 consists of what? Two elements. There's two answers, plus or minus 4i. The square root of negative 16, however, is uniquely valued. Okay, it is 4i and only 4i. But you've seen this type of thing in the real situation also. If I said z squared equals 16, you would say the answer is what? Plus or minus 4 for the two answers here. Okay. But at the same time, we say the square root of 16 is just 4 and only 4. Okay? Okay, that's the real case over here. All right? All right, so just keep that in mind. Solve z squared equals negative 7. That would be what then? Plus or minus I times the square root of 7. And you could use your calculator to compute so many decimal places accuracy to the square root of 7. Or I'm perfectly fine with you just leaving it this way. Okay, unless otherwise stated. Alrighty, I want to talk about the powers of I now. Now we're going to do this just like usual. You remember any non-zero number to the 0 power is 1. That still holds. This is to make our rules of exponents consistent. Okay, I to the first power is just going to be I, just like anything else. X to the first power is X, right? Regardless of what X is. Okay, same thing holds with I here. I squared is negative 1. We're already familiar with that. That's the way we defined I, really. Okay. Well, we actually defined it the square root of negative 1, but I squared would be negative 1. Now let's go to I cubed. That is new. I to the third power should be what? I squared times I to the first, right? With a common base, you add the exponents. 2 and 1 is 3, so these should be equal. That should be a valid equal sign. If the rules of exponents are going to hold for these imaginary and complex numbers, okay, that would have to hold, and we're going to force them to hold. Okay, so I squared, though, is negative 1, so that's negative 1 times I to the first, so that's negative 1 times I. That's more compactly written as negative I. Okay, so I cubed is negative I. I to the fourth, let's break it down this way. How about I squared times I squared? But you remember I squared is negative 1, so that's negative 1 times negative 1 is positive 1. So I to the fourth is 1. I to the fifth, however, would be I to the fourth times I to the first. I to the fourth is 1, so you see, really, it's just going to be exactly the same as I to the first power. Okay, I to the first power is, of course, what? I. Okay, I to the sixth, again, pick off that fourth power. That's going to be I to the fourth times I squared. I to the fourth is 1. Multiplying by 1 doesn't change whatever you're multiplying on. So I to the sixth is the same as I squared. I squared is negative 1. Okay, so there you go. Now what I'm going to do is write down what you see here, which is a sequence of numbers that is periodic with a period of 4. When I say periodic, I mean with a period of 4, it means it repeats itself after every 4 elements in the sequence. Now you could start at the 0th power like I've done here, but you may not want to. You could start at the first power. Okay, but if we start at the 0th power, we'd have what? 0, I to the 0 is 1. There's the first power, I. There's the second power, negative 1. There's the third power, negative I. And then here's the fourth power. We're back to 1. And then remember, at each stage, you're multiplying by I, right? Because these are just the powers of I. So the next one would be 1 times I is I. And we also saw that up here. Okay. Next one would be multiplied by I again. You get negative 1, right? Because it would be negative I squared. Multiply by I again, you get negative I. Multiply by I again, you get negative I squared, which is negative 1 is positive 1, and you're back where you started, so it goes back to I, negative 1, negative I. Okay, so you can see this pattern in the powers of I. It's a, what, a periodic sequence with a period of 4. You can only get what out of a power of I? And I'm talking about, you know, actually ends up being integral powers of I, so any integers. Okay, you get what, 1, I, negative 1, or negative I, and that's it. Okay? All right? Now, I'm only going to stick about to positive integral powers here. Okay, not negative powers. I will address negative integer powers in a separate video, the next video. Okay? To find a positive integral power of I, we need only consider the remainder of this power, or this exponent, upon division by 4. And we saw that sort of thing happening right up here with the 5th power and the 6th power. Okay? All right, why? Well, that's because we have this periodic behavior in this sequence of powers of I. Okay, I'm going to show you formally why we're only going to be concerned about the remainder upon division by 4 for the power. Let's do this. I to the 23rd power. Okay, I want to find what it is. Okay, I could go all the way out in the table until I found what? The 23rd power. But that's going to be time consuming here, so let's have a shortcut. Okay, the first calculation I'm going to do here is go 23 and divide it by 4. You see the quotient is 5, which I'm not really concerned with, but this is what I'm really concerned with, the remainder, 3. Okay, all right, so 23 is actually 4 times 5 and then 3 left over. Okay, so you could imagine this. If you were going to go out to the 23rd power, starting at the first, you could count out till you get to the 23rd power, or you could think about this 5 represents, you would go through that sequence, that period, 5 times, and then go what? To 3 left over. So you go 1, 2, 3. So it ought to be negative I. Okay? So it ought to be negative I. It should be the same as I to the 3rd power. Okay? All right, we will see this formally using formal rules of exponents here. But we agreed from this calculation right here, 23 is 4 times 5 plus 3. Sure is. There's its remainder sticking out on the end. Remember, the remainder upon division by 4, the division can be done in such a way that the remainder is always either what? 0, 1, 2, or 3. Right? All righty? All right, I to the 23rd, look at this statement right here. I to the 23rd is I to the 4 times 5 plus 3. Okay, I just transcribed there. Now, that's I to the 4 times 5 times I to the 3rd, right? Why? Because these have a common base. You would add the exponents and you'd be right back here. Okay. So those must be equal, so that's a valid equal sign. Okay. Now, I'll just let that I to the 3rd power sit there for a bit. I to the 4 times 5. Do you remember this property? If I've got a base and I raise it to an exponent and then raise that result to an exponent, what I can actually do is multiply the 2 exponents. Okay? Then I could say that's really I to the 4th all to the 5th power. Because to do that, I would go I to the 4 times 5, but that's just what I have right up here. Okay? But the reason I like to look at it this way is we remember that I to the 4th power was what? 1. Okay, we showed that up here. Remember? I to the 4th power, well, that's 1. Okay? That's nice because multiplying by 1 is super easy, right? Okay? So this is really what? 1 to the 5th power, which any power of 1 is still 1. So we've really got 1 to the 5th power times I cubed is I cubed. And there's my justification. Do you see? When I went I to the 23rd, it's actually equal to I to the remainder upon division by 4. And that remainder turns out to be 3 in this case. So that's the same as I cubed. I could say that right off. Now, what was I cubed? It's negative I. Okay? Alrighty, so there you go. Let's talk about a slightly larger number for the exponent. 2,137. Okay, I'm going to show you what the calculation would be in that case. I've got 2,137. I'm going to divide that by 4, and I got 534 as a quotient with 1 left over. Okay, now doing a calculation similar to what I did up here, but in my head, you know, I'm not going to do it every time. I can see that I'm really going to have what? I to the remainder power in the end. Okay? All right? This would actually be 1 to the 534th times I to the 1st. But I to the 534th power is still 1. So there's no point in having that there. Okay? What's I to the 1st power? That's I. Okay? So you just need that remainder upon division by 4. Okay, and this works no matter how large the exponent is. But here, I'm going to show you here that we can shorten our work even more. Okay, even this calculation is longer than I need it to be. Okay, all right, I to the whatever, okay, 37063855490132. Okay, I wouldn't want to begin to read that as a proper number. Probably could, but I'm not going to. Okay, instead of dividing this gigantic exponent by 4, like I did up here, I'm going to just show you a little reasoning we can use here that we don't have to do all that much. Okay, I'm going to have you just note here. See that big old giant exponent, 370 blah 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 1342 is what it ends in here. This is 3706385549013300 plus 42. Okay, you agree that's true? Okay. All I did was pick off the last two, the tens place and the ones place, okay? I just picked those off there. So I've got these two decimal places for the difference would be zeros, right? Okay, but wait a minute. This number right here, you can see, because it ends in 2 zeros, would actually be 37063855490113 times 100. Okay, because multiplying by 100, what do you do in decimals? Just put 2 zeros at the end. Bam, that's the number we have right above. And then, of course, to make that equal, we've still got the plus 42 at the end. Now, remember, I was going to divide this thing by 4, and all I'm worried about is the remainder. I don't care about the quotient particularly. Okay, I'm going to point out here that this big monster here, this is a multiple of 4. Why is this thing a multiple of 4? I'm talking about the product here when I multiply these. Or if you want to, this number above here, this guy that I'm circling now. That's a multiple of 4. How do I know that? Well, because if I was to divide this thing by 4, I could just do this. I could divide the 4 into this factor, the 100, and it goes in evenly. 100 is divisible by 4, isn't it? It's 25, right? Okay. That means if I was to take this part of it, I would get a remainder of 0 when I divided that by 4, right? That's not very interesting. That's not going to really help me. If I want to find the remainder to the whole thing, this number divided by 4, what I should do is just divide the last 2 digits by 4, then we should find that remainder. Okay, and that'll be the remainder for the whole big exponent there, okay? So what I'm saying in the end is to find the remainder of this exponent upon division by 4, we need only consider the last 2 digits. So if I go like this, I to the 370 blah 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 1342, that's going to be exactly the same as I to the 42 power. Just pick off the last 2 digits there, okay? Because everything, there'd be zeros there for the other part, and that would be divisible by 100. So, okay, or by 4, okay, because it's a multiple of 100. So that's I to the 42, and then let's do that calculation with 42. That goes in 10 times. The remainder is 2, so this is the same as I squared. I squared is -1. Bam, we got it. Okay, alrighty, so that makes it much, much easier when you're finding powers of I. So here's the rule. To raise I to a positive integral power, okay, again, this actually works for negative ones, but students screw up the calculation with negative integral powers. So in the next video, I'm going to show you how to do it a little more simply with the negative integral powers. Okay, but anyways, to raise I to a positive integral power, ignore all digits except the last 2. Find the remainder upon division by 4 of this number here from part A, so the last 2 digits, and then raise I to that remainder power, okay? And you're done. Okay, so I've got I to this big monster power, okay? Whatever it is, what do I have to do? Well, all I do is what? Pick off the last two digits. This thing's going to be the same as I to the 11th power. But I'm not even going to write that. I'm going to go 11 divided by 4 is 2. Let's see, that gives me 8. 3 left over, okay? So this is the same as I cubed, which is negative I. Voila. Okay? All right, so there you go. I hope you understood all that stuff. We'll continue with complex numbers in the next video.